All right, so the meeting is now recorded, so we can start. Hello, everyone. Welcome to episode 35 of Warsaw Quantum Computing Group meetups. Today we host a fantastic speaker, Dr. Katarzyna Rycerz, and she will give a lecture titled Using Quantum Devices for Workflows, Scheduling Problem in EuroHPC PL project. Before we start, we would like to thank our strategic partners, Snarto and Cogit, for supporting us, and our honorary partners for helping us in advertising this event. As you can see, recently a new honorary partner has joined us, Qubit, which is a students association from Warsaw University of Technology. Yeah, our partners help us a lot. So we are very happy that there are so many institutions. Yeah, I think that we are ready. So as usual, this meeting is recorded. So hopefully the video will be later available on our YouTube channel. If you have any questions, we've agreed with Katarzyna that you can interrupt during the lecture. You can try to ask your questions during the lecture. This lecture will be more interactive, but you can also post your questions on our chat, and there will be a Q&A session at the end. So I think that's all from my side. So Kasia, if you are ready, the Zoom is yours and you can start sharing your screen.
Yeah, okay. So hello everyone. I'm very happy that you to present the work, which is in fact done in a team which is formed between the Institute of Computer Science and Cyfronet in IGH in Kraków. I would like to say a few words about the actual optimization problem we are trying to solve on using quantum computer. And this optimization problem comes from the applied computer science. And it is actually something that was in applied computer science for quite a long time. And now we are trying to also to check if quantum computers are good for solving such problems, and if they can be useful. Okay, so first I will say a few words about this EuroHPC PL project. The aim of the project is adjust research problems and software to the capabilities of the new architectures. And these architectures, should be hybrid, because most of them will be hybrid in the future, I think. There will be traditional supercomputers, high-performance computing machines. Then we have quantum computers, and we have also neuromorphic accelerators in the project, although I'm not involved in this neuromorphic accelerators. But yes, we also have this kind of we want to build this kind of infrastructure. And our idea is to support large-scale applications that will use this kind of infrastructure. Okay, and in this project there are many different partners. This is a Polish project, but it's a part of European EuroHPC joint undertaking. So it's a part of European initiative, but it's the Polish part. Okay, and the problem we are trying to solve is, as you already saw in the title of the talk, workflows. What are workflows anyway? Workflows are applications that are built from so-called tasks, and these tasks are should be executed in the well-defined order, and this order is defined by directed acyclic graphs. So you cannot make a cycle. So for example, the first workflow with letter A, you first have to start the yellow tasks, then blue tasks, then after the blue task finish, you start a red task, etc. So you have the graph of execution, and you have tasks which can differ from each other, and you have resources. And then there are different problems how to efficiently run these tasks. And you can think of many different problems, optimization problems for execution such applications, which are usually NP-hard. Okay, and to show you example applications, you can see that there are real life applications like, for example, montage, which is analyzing of telescope images, or some seismic hazard maps. And I will show you some. There are publications, of course, but I will show you maybe. So, okay, I will show you. This maybe it's better to see it on the web. So this is a WF Commons web page of the community, of workflow community. And as you can see, there are different instances of workflows, and here is the architecture of this initiative, and you can see that you have production workflow management system, which are the real workflow management system that execute thousands of tasks connected in this directed acyclic graph. You can have a logs of this execution, so you have real data of execution of your workflows, but you can also have a workflow generator that generates some realistic synthetic workflows with certain assumptions like distribution, probability, etc. So this is a very good source of data for us. To show you some data, you can look, for example, workflow instances, and here you have, you can see there are three main workflow execution systems, Makeflow, Nextflow, and Pegasus. Pegasus, I think, is the most popular one. You can see different fields, like you have workflows from bioinformatics, agroeconomics, astronomy, seismology, etc. And you can see, for example, here, if you look at the repository, like this montage, you can see here how the structure of the workflow looks like, what's the publications about this structure, this workflows, and also you can of course see the actual workflow logs. So for example, here you have a log written in a certain language based on JSON, when you have where the workflow was executed, what machines were involved, and what kind of tasks you have. And you have also information about memory, CPU, so all that stuff that you can optimize if you want. That's actually source of data for us. And our goal in the EuroHPC project is to join this this real workflow examples with the abilities of quantum computers, which is quite challenging because quantum computers are not yet are in early stage, and all we can try is to run small examples, which I will show you later on. But there is a still chance that we manage to at least show how it's possible to join this real world with quantum computers. Okay, so going back to our presentation. Okay, so we plan what we are planning. What's the architecture of our system we would like to build? So as I said, we have our problem looks like this. We have a workflow, definition of the workflow, and we have description of resources. And then what we want to have a plan, the real plan, where we actually, in the plan we will say that the first task is executed on the resource 1, this task is executed on the resource 2, etc. So this is a real plan to execute. And to produce this plan, we are planning, or we are already using, but we are in the process of making that more usable. We are using quantum computers, so D-Wave, and also as an option the gate computers like IBM. So variational algorithms, and of course we are also using classical solvers because classical solvers are good as reference methods to check if to check if the results are okay. At least at this stage, it's very we need that, yes. And for this classical solver, we are using the classical high performance computers like Prometheus at Cyfronet. We plan to make the interface to our system using Jupyter notebooks, which you can also run directly on supercomputer Prometheus. And then you, as a data, we first use test problems, which I will show you later on, but we are also in a process of applying this to real examples of workflow management systems. Those from Workflow Hub I just showed you. Okay, and then what's our problem? So of course you can define, having this data and having this workflow definition, you can define different optimization problem, but we focus on one of this optimization problem just to have something to start with and to focus on something, okay? So our problem looks like this. We have a directed acyclic graph. For each task, we have a time matrix and cost matrix. So we know how much time each task will take to run on each machine, and how many cost units you have to pay for it. We assume the model you usually have in clouds when you have machine types. And you have normally you have a finite number of machine types, but each machine type has to have many different instances. So we assume here we have, we for example can have, for each task we can have the same machine type, and they will not interfere because they are on different instances. But the machine types are finite number, and this machine really means machine type, yes? But this, of course, can be changed. It's just our assumption to focus on something. So we have cost matrix, time matrix, and we have a deadline. And our goal is to minimize cost, and our constraint is to fulfill a deadline. Of course, you can take it the other way around, try to minimize deadline and fulfill certain cost, not to extend certain amount of money. But we actually focus on this specific problem. Okay. So how are we going to do that? So as you probably know, quantum computers understand if you want to make the optimization, you have to build a function, quadratic function, to tell quantum computer to optimize it. And so once we have this conditions and this data on workflow, how to put it in the quantum computer. So we decided to do it in the way that first we define our problems as a binary integer linear problem. How this binary integer linear problem looks like? Well, you have to have cost function which is linear. It's binary. That means that solution to the problem is a binary string, a binary vector. So you have a cost function that is linear to this binary vector, and also you can have constraints, and these constraints are also linear. So this is the first step. We define the workflow problem as a binary integer linear problem. Once we have it, it's not enough because we need to produce quadratic function, because that's what quantum computer understands. But it's very easy to produce from BILP this quadratic function, and I just put the prescription on this slide. To be precise, cost function stays the same. You just rewrite it in the way that it will become quadratic. It's very, very easy because x is only 0 and 1. So 0 squared is 0, 1 squared is 1. So you can easily rewrite it that way. And the more complicated is what to do with this constraint. So instead of solving this system of equation, you are building a vector ax minus b, and you minimize the length of this vector. To be more precise, you minimize not the length, but the inner product of this vector, which is roughly the same. So you build inner vector from this, inner product from this vector, which become a quadratic function, and then you want to minimize that. So in fact, you minimize two things: this cost function and this inner product of the vector built from your constraint. The problem here is that you have to somehow put weight that tells quantum computer how important is your constraint in comparison to the cost function. Because if this you call that penalty, this coefficient, and if you put it very small, then the quantum computer will take into account only minimizing the cost function. And if you put it too big, then the quantum computer will try to satisfy the constraint and will not take into account your cost function. Therefore, this penalty should be somehow balanced. Of course, and one more thing just for the record, because I think most of you know it, instead of giving quadratic function and looking for minimal value of a quadratic function, you can also rephrase your problem and write it in the form of so-called Hamiltonian. And for that, you have a very simple prescription already. So it's nothing really difficult. You just have to apply this prescription. The only thing that I think is worth to saying that here, the Hamiltonian is mostly used by physicists, and you are searching for minimal, you are searching for eigenvector for which eigenvalue is minimal. And here in Cubo, you are searching for argument of the function for which the function is minimal. So argument of this function corresponds to eigenvector of Hamiltonian, and value of this function corresponds to eigenvalue for this eigenvector. But there are either you can give this, describe your problem this way, and this way you will get the same answer. Okay, this was just for the record. And then your problem can be, you can code your problem or the work problem in different ways, but here I will show you just a very simple, the simplest coding. Of course, my former Master of Science students, Julia Plewa and Joanna Sienko, investigate different codings, and they will tell you hopefully on some of next seminars how to do that. But here I will just show you how to do this first simplest coding. So you just take tasks in the, you make a kind of matrix that you have tasks and machines. And for example, and you number binary variables in that way. For example, x1, if x1 is 0, means that task number 1 is not assigned to machine number 0, and if x1 is 1, then task number 1 is assigned to machine number 0. And the cost function is very easily to build, having this coding, because as you see, you have a just cost matrix, which looks the same as this this binary variables matrix, and you just multiply the cost by the binary variable. So if binary variable is 0, the cost doesn't count, and if binary variable is 1, the cost is included into the whole function, and that's how you calculate the whole cost. It's not very difficult. Then you have to add 2 constraints. First constraint is a constraint that you cannot assign task to more than 1 machine, and you have to assign task to some machine. So for each column in this table, you can have in each column you can have only one. You cannot have 2 ones, because it would mean that task 0 is assigned to both machines 0 and 1, which is not possible. You have only one, and this one should be present, no 2 zeros, yes, because that would mean that task number 0 is not assigned to anything. Okay, so for that you just build this constraint in linear way. So you have to build a matrix, and this matrix looks that way, that each row you have as many rows as tasks, and for each row you remember these places where the task is assigned to the machine. This particular task assigned to this row is assigned to this machine, and if you calculate once, it should be only one, because you should be only one assignment for this task to the machine, and this can be written as this linear system of equations that way. It should be equal to 1. There should be only one. And we have also deadline constraint, which is more difficult because you have inequality. So you build a matrix. You have as many rows as paths. in your directed acyclic graph. And each path should have, time of each path should not exceed deadline. So you calculate, in each row, you calculate the time of each path, yes, every path. So you put in this matrix, you put time in each row. For example, in row of path, first path, you put times, but only in these places when the task is actually in this path. Because if the task is not included in the path, you put 0, yes? And that way you can calculate in each row the time of each path. It should be less or equal to deadline vector. And this is, well, this is a nightmare for in our problem. It doesn't look that suspicious, but in fact, you cannot put this inequality to quantum computer directly. You have to somehow use some tricks for changing this inequality to equality. And we are using very simple way, just add variables called slack variables, which means you have to add a non-zero zero or on greater than 0 variable that is this difference between your time and the deadline, yes? And you code this difference using binary encoding, that's it. So this is how we are doing that, but it's not very very advanced, and it causes some problems we are trying to overcome now. Okay, and now just for the record, I'm writing again this objective function, machine usage constraint and deadline constraint, but as a quadratic functions according to what I already showed you, so according to this prescription. Okay, so you build your, we build our QUBO like this, and one more thing which is important, we have to set up weights. Yes, so weight for cost function, for machine usage, and for deadline constraint, just to make them in balance. So the quantum computer will take everything into the account, which is not that easy, actually. Okay.
Kasia, may I interrupt you? Because I can see that Adam has raised the hand.
Yeah, it would be nice if you can moderate, because I cannot, when I'm talking, I'm not paying attention to
Yes, that's my role. That's why I interrupted. Adam, would you like to ask a question? You can unmute yourself.
Thank you. Do you hear me?
Yes, we can hear you.
Okay, great. I have just a question about the deadline constraint, because there's the sum from W equal to 0 to P minus 1. Over what we are exactly iterating? Is it that all possible paths from the possible first node to the possible end node?
Yes, yes. All the possible paths, yes. Mm-hmm. So if you have a lot of paths, it's a disaster. I agree.
So the question is that do all of them have the same deadline, or each node has its own deadline, or how it works?
Yeah, so we assume all them have the same deadline, because we want to fulfill the deadline for the whole workflow. So every path have to fulfill the deadline. But in our description of the problem, it's not a problem because this is a vector of deadlines, and this vector of deadlines actually is built in the way that it has the same value on each in each place. Yes, so we just simply repeating the same deadline in a row. In a column, but you can change that. You can put different deadlines. It's not. It will work the same way, but I'm not sure if it will have practical meaning, because you want to have the whole workflow ended. If there will be a practical meaning of such problem, then it
I'm fine with this practical problem. There was a question, not a question how you did it, not how it can be done. But then I have another question. How the number of possible paths grows with the size of the problem? I feel like it can be even exponential in the size, in the number of tasks.
Number of tasks? Well, it depends on the actual workflow. Type of workflow, yes. So you can, yeah. So I don't know the general answer to that, and we, to be honest, we haven't done any analysis on that. But as far as I looked, you can look for that. You can look to have some at least some idea. there are, so I guess that here, for example, for this montage, you can have many, you can grow, for example, you can increase blue, sorry, not blue, greens, and this.
So kind of each layer,
like
the first group.
Yeah.
Then it can grow a little bit like exponentially, right?
Yeah, I think it can grow, yes, but this, for example, the red one will not grow. So
yes.
Yeah, so it depends, but this comes from the actual montage workflow structure, which is I think is kind of some image recognition or something. So it depends on the actual application. We can look at the other one, maybe seismology. Seismology is very simple like this. So well, it depends. Yes, I don't know if there is a general rule for that.
I think I have an idea about this, but maybe let's move it to the end of the presentation.
Okay. So okay, so that's how our cost function looks like. And now I will come to the next part of my talk. So saying how we were trying to solve it on both computers. So gate model computers and quantum annealer, which is in fact the D-Wave. I think all of you are familiar that we have these two kinds of computers. So maybe I will not tell a lot about this. So first I will say a few words how we are doing that on D-Wave. So D-Wave is just for the record. I will recall you that D-Wave works in the way that we actually, what we are providing to D-Wave, we're providing our Hamiltonian of our problem, or QUBO. QUBO can be transformed to the Hamiltonian, and then the D-Wave ordered way that it starts from initial Hamiltonian, from which all the possibilities are equally probable. It's with equal probability, and it starts with the minimal energy of this initial Hamiltonian. Then it slowly is trying to move to our Hamiltonian, the final Hamiltonian. And the idea is that in ideal world, the system should stay in this minimal energy through the whole process. And if it's done quite slowly, it can happen that it will really work. So the system will end up in a final Hamiltonian and still in a minimal energy system. So we will minimal energy state. So we'll learn the minimal energy state, and that would be solution to our problem. But in practice, of course, it won't. It will not always work that easy. But yes, at least this is the idea how it works. Okay. So what to do? First, if you have such a problem as ours, you have to formulate the problem as QUBO or as a Hamiltonian. Then you have to match the QUBO with the annealer architecture, which is one step that it's not maybe that necessary. It's not on the gate computers. You don't pay that much attention to that because then you have other layers that are doing that. But here you have to think of that also. And then you obtain the results, and you unembed the results into your initial QUBO, and you reverse your QUBO into the actual problem. So you have to understand what the output is. Okay, and the only thing that has to be explained is how to match the QUBO with the architecture. So this is an old architecture of D-Wave, which was called Chimera. And we were doing that manually at that time, but now it's Pegasus, and in Pegasus, correct me if I'm wrong, but I think in Pegasus it's very difficult to do that manually, and there are tools for doing that automatically. But the idea behind this matching your QUBO to the architecture of the quantum computer is very simple. So assume that you have QUBO like this. So you have a squared minus a squared minus b squared minus c squared. This coefficient of QUBO minus ones are assigned to it with your vertices of this graph, and you have edges of this graph, and these edges are actually assign there is an edge between two vertices if the product is part of your cubo. So you have a product 2 times A times B. So you have an edge A times B. You have an edge with weight 2. And that's why that's how you can instead of having cubo formulation, you can have visual graph. It's the same information, but the different view of it. So once you have a visual graph, you have to somehow fit it into the architecture of your computer. And if you are not lucky, and usually you are not lucky, the architecture is different. Like you have a triangle here and you have a square here. So how to fit triangle into the square? So you are doing also a trick that you are choosing one of these variables. Here is B. And you are saying that this B should be represented by 2 different physical qubits, like 0 and 5. And so they are both representing your variable B. Of course, if you get an answer and in zeros, qubit 0 will be different value than in qubit 5, then you have a problem, yes? And this is called these qubits that represent the same value are called chain. And if something wrong happens and they don't have the same value, you call that chain is broken. Okay, so that's actually how you are doing that in D-Wave. You have to add the constraint that these 2 variables have to be the same to your cubo. So your cubo becomes more and more complicated. And you have to somehow give also the penalty value to this constraint. It's called a chain strength. Okay, just to focus on the results, we renamed the name of the weights because this is just because I will present the results, so you will know what P and S means. So we assume that weight associated with cost function is 1. So we don't manipulate here any weights. Then you have a weight that tells you how both constraints are comparable with a cost function, and this is this P. And then you have weights that are saying how mass and usage constraint is in relation to deadline constraint, and we call it that S. And if you look at that weight, this constraint, mass and usage constraint, if you look in the matrices here, this matrix have smaller values because there you can have only 1s and 0s. And here, in deadline constraint, you have times. So times can be bigger, yes? So after calculating all that, it's good to have, well, this will have greater impact if we don't balance it with this S penalty. Okay, and these are problems we actually put into the D-Wave. You can see that they are very small in comparison to this big production workflows. So there is still a gap we have to fulfill, but we managed to get at least some results. At that time, we were trying to find these weights by maybe not a kind of educated guess and trial and error method using classical solver. So first we were putting cubo to classical solver, find the best P and S, and then we're putting that into the D-Wave. These are the actual values on PS and chain strength found for these problems that worked, that were the best. And here are the results. So as you can see, EuroHPC found solutions for these 3 problems, and for 4 problems was not possible to find, mainly because of the embedding, which is actually additional requirement for qubits. Because for unembedded cubo, it found the solution. And as you can see, the real D-Wave, real machine found solution for two problems, 2 most simple problems. For third problem, it didn't found the optimal solution, but it found quite close solution with deadline with 35 cost units, when minimal is 40. So we'll pay 5 units more if you use D-Wave. For the fourth problem, it didn't find any solution and even wasn't close. And these are also energy histograms showing how many correct answer, more or less, we get from the output of the samples. This work was actually done and presented at ICCS conference. And since then, we made a lot of research. Mainly, we changed Chimera into Pegasus, but we observed that Pegasus is quite noisy because the architecture is dense and it didn't produce better results, which was a bit disappointing. But at least now I cannot show you more exciting results. What we found out, we also were trying this D-Wave hybrid libraries, but we found out that in D-Wave hybrid you can define paths of execution, and for example, you can define that you are using D-Wave quantum computer machine, but you can also use add additional path like simulated annealing or taboo search, so classical algorithms. And we found out that this classical algorithm always overcome the result from D-Wave and was chosen by this hybrid for further execution. So it wasn't very satisfying result, but then later, just recently, we put our problem into a new hybrid solver recently given by D-Wave, which is called CQM, and this CQM produces promising results. So we are now investigating how it really works and why it produces better results than the previous solvers. But I can tell you that the CQM is quite promising, at least from our point of view, because we managed to already to translate the real workflow from workflow commons, one of the smallest workflows, into the CQM. It has more binary variables than just a few, and it looks that it works, at least at the beginning. So we'll see, and maybe I will inform you after some time that we get some results I can show you. Okay, and then I will tell you now what we achieve on the gate model computers, mainly IBM, although we are mostly working with simulators because these publicly available gate machines are not good enough to achieve an satisfying result. So we focus on two variational algorithms. The idea behind variational algorithm is that you build a parameterized circuit called ansatz, and you're steering this parameterized circuit with a classical computer. So you can describe it in a way that you are changing the parameters of the circuit and see what's measure the output. Based on that output, you calculate expectation value of your Hamiltonian, and you are trying to change these parameters to minimize this expectation value of your Hamiltonian. So the minimal average energy for your Hamiltonian. And you have variational principle that ensures that this expectation value is always greater than the smallest eigenvalue. So you can do that, and you can hopefully achieve the lower bound of your expectation value. Okay, so maybe I will show you a small demo, because describing this working this variational algorithm is always a problem because they are quite complicated. I think if you look at the demo, maybe it will be more easy to understand. So I built very simple problem. You can see that it has two coefficients, 2 and 1. And this sigma z's, they have two eigenvalues, 1 and -1. So if the solution is 0, 0, the eigenvalue is 3. You can easily calculate that using this prescription. If the solution is 1, 1, the value is -3, and for 0, 1, 1, 0, it's this way. Okay, so once you have this cost function or Hamiltonian you want to minimize, how your variational algorithm is working. Okay, so I did it in this quantum composer to show you. I'm not sure if it will be, it has some didactic potential, but maybe it is. Okay, so how this initial circuit looks like for your, I'm showing now you QAOA, so so the algorithm that you built this initial circuit in certain way. First, you put Hadamard gates, which you just produce every, we produce a state where every solution is equally probable, with equal probability. So either 0, 0, 0, 1, 1, 0, and 1, 1 are equally probable. Okay, and then you put the Hamiltonian of your problem. How you do that? You are using RZ rotation around Z axis gates. And all you need to know, at least now, is that you put your these coefficients in your Hamiltonian are 2 and 1. So you put them here. It's 1 and 2. So these are coefficients from your problem. And here is P divided by 4. This P divided by 4 is an angle. It's a parameter you change. So I'm now a classical optimizer. And all I can do is to change this angle, P divided by 4, into different one. Of course, in this algorithm, both angles have to be the same here, but I can change it. Okay, and I will see what's going on. Okay, so once I have it, I can look at the output, and I'm in a lucky position because I have a simulator here, so I can preview a state vector. Normally, if I do a measurement, I will not get any results because, as you can see, all these solutions are equally probable. So you can, so there is no real outcome. But I can look into the state vector and see what's going on. Look at 0, 0. You look at 0, 0, and you look at phase angle. You can see that this phase is related to the output of your function because you have 3 here. 3 P divided by 8. For 0, 1, you have P divided by 8. So you have 1 times P divided by 8. And this 3 and this 1 corresponds actually to this 3 and this 1. And why is here P divided by 8? Well, it comes from the definition of rotation gate, because here you gave angle P divided by 4. But if you look at the, if you look at the glossary, you can see that the definition of the RZ gates is you have to divide this angle by half. So you have normally you have pi divided by 4 and divided by 2. Okay, so now if you look at your output, of your angle, your phase, it's 3 P divided by 8, 1 times P divided by 8, and here you have 15 pi divided by 8. Why 15? Well, this 15 is the same as -1 because you can add or subtract 2 pi from it and you will have -1. So it's the same as minus pi divided by 8. And this minus pi corresponds to this -1. And for -3, you get 13, yes, 13 pi. If you subtract 2 pi, you will get -3 pi divided by 8. What I'm going to say is that the value of your function for this argument, so for 0, 0, for 0, 1, 1, 0, 1, 1, is encoded in the phase. And the classical computer classical algorithm can change this parameter angle into different. Like, for example, let's change it to smaller angle. If you change it to smaller angle, you see that the phases are similar because the colors are similar. So if this angle is small, the difference between phases of your solutions are close to each other. And if the angles are bigger, then the distance is bigger. Yes, you have different colors. But if you put too big angle here, it will make no use because 2 pi is the same as 0. Yes, everything goes around. So that's why saying what kind of angle should be there, it's difficult. That's why a classical optimizer has to do some numerical procedure to find out what angle to put to get the right results. Okay, but as I said, it's not the only thing you can have to do, because as you can see, the amplitude of the whole states is the same, and the measurement will not give you any result. Therefore, you need another layer, another Hamiltonian, which is called mixer Hamiltonian. And this mixer Hamiltonian is, the goal of this mixer Hamiltonian is to translate the phases you had into the, something is so. Okay, good. To translate your phases into the amplitudes. So now you can see that if I gave Rx gates, my solutions are not equally probable anymore, and I managed to sort them. So the 1,1, which has the smallest eigenvalue, is the most probable. Yes, it has 64 probability to obtain it during measurement. Yes, and 0, 0, which has the biggest eigenvalue, is the least probable. Yes, it's only 3.6% to obtain. So by manipulating the angles of your mixer Hamiltonian, you can decide which state is the less probable and more probable. And you can see it's not that easy, because if I put minuses here, so I will change this angles in the other way around, the solutions are sorted in completely different way. This solution is not satisfying for me, because I wanted 1,1 to be the most probable, because it has the smallest eigenvalue. And this solution, this solution is not good for me. Yes, and that's what classical part of the algorithm do. It calculates, it takes this outcome, the histogram from the output, from measurement. It calculates the average eigenvalue, the average of this output, and then it decides how to change these angles to get smaller average value. And that's how it works. And what you can do, you can repeat this again. And these are called layers. Yes, you can repeat this, and then you can change. Each layer can have different angles. This gives more possibility to classical algorithm to change and to produce right results. Okay, so that's how it works. So what we did for our workflow problem. There are actually two algorithms, as I said. I showed you this QA-OA algorithm, but you have also another option using variational quantum eigensolver VQA algorithm. And the difference between them is that this QA-OA are used usually for combinatorial problems, so the problem as we have. And this VQA is mostly used in computational chemistry for finding ground state of molecules. And it works with more general Hamiltonians, because you can have, in QA-OA, they are usually diagonal. You have only Pauli matrices Z, and here you have different Pauli matrices. But with ansatz, so with this starting parameterized quantum circuit, you can have for VQA, you can have anything that fits, and they differ match for different molecules. And for QAOA, you have the specific prescription with problem and mixer Hamiltonian. But with ansatz parameters, they are growing much more quicker than with QAOA, because here you have only 2 per each level, as I show you. And with measurement for VQA, you have to, it's more complicated because you have to measure in different, usually measure in different bases, and for QAOA, you measure in Z basis. That's basically the difference. And now we took, when we started with our workflow problem, we first, although QAOA seems to be more suited for our problem, we started with VQA. Why? Because it looks simpler at the first glance, because you don't need to look at this to understand this ansatz. And so we started with VQA, and our first results are actually with VQA. As you can see, the workflow was very simple. But we managed, by manipulating these weights and using as a reference solver simple Python eigensolver, we managed to find out setting that allowed us to get well, satisfactory result, because we managed to get actually optimal solutions, yes, on Quast simulator. But I would say that was just like guessing the parameters. So it's not a way that you should do this, because normally you should have some kind of procedure that you know what to set basing on your problem. And here it was just a trial and error method. That's why later on, our former students, Joasia Plewa and Asia Sieńko, who will present it in more detail, will look into that more I would say more not specific, but more
detailed.
Sorry?
More detailed.
More detailed, but maybe how. Sorry, I forgot the word, but I have it here.
You can say it in Polish and we can try to help.
Okay, uporządkowaną.
Ordered?
Maybe ordered. But more general, the way that you can somehow know how to put things on, yes? And they did a lot of work. So they they changed encoding. So they managed to use less qubits, but a bigger problem. Yes. So and they will tell you more about that. But they managed to fit larger problem into the less qubit architecture. Actually, they have a problem that fits into 15 qubits that they plan to run on this IBM Q Melbourne. But in the meantime, this IBM Q Melbourne was switched off. So that was kind of disappointing, but still they managed to run a bigger problem than this one. Yes, and they will tell you if you come to their talk, they will tell you how to do this. And they were also experimenting with different mixers. They will tell you a mixer allows you to search through the space of solutions by if you choose this in appropriate way, you will get, you don't need to care about the solutions that are not correct at all, that don't have a meaningful information. But this is more, I will have to go in more details, that's not necessary because they would be separate talk. So what they did, they were actually select this initial parameters with uniform distribution, and they were calculating some statistics for chosen metrics. And they, in that way, they compared different optimization method, different coding, and different algorithms. That what the work was about. But still, they didn't find a way how to select these initial parameters in such a way that we actually optimize our workflow problem. That work is continued by Justyna Zawalska, who was already on this seminar, and she's trying to find out more educated way how to find this angles, how to find these parameters in order to actually minimize our problem. But it still needs more work. That's what I wanted to say. Here I put the settings that you have to really set up when you want to get your results from a quantum computer. So it's not enough if you have this quadratic function, you also have to think about weights for your problem, about initial ansatz parameters, about choice of classical optimizer. So there are many things you have to choose. And it's really, there is no yet how to say the roadmap, how to do it correctly for many problems. So there are still many open questions. And I think that's it. After we managed to get systematic method for obtaining this minimal value, minimal solution for our problem, we can think also about experiments with noise model, because still all our experiments are on using simulators, at least for gate computers. So once we have a right way of doing that with simulators, we can try also how to use these noisy devices. But it's the next step. And what we are really thinking about also is this dedicated work-await hybrid method. So the method which is hybrid, but on the level of workflow. So the method that knows the workflow structure and divides the problem into smaller pieces, knowing that it's workflow, not on the level of QUBO, but above. But this is still only the idea now, so we don't have real results. And I think that's it. Thank you very much.
Okay, great. Thank you, Kasia. Very interesting and inspiring talk with many interesting takeaways. I saw that Adam had his hand raised. So Adam, would you like to ask a question now?
Actually, I have so many questions that maybe if there's another person who would like to ask something, could go first.
Okay.
Like I have already 4 questions. So.
All right. Do we have any more questions? Does anyone else would like to ask something?
Well, I don't know if there was understandable, because I was trying to explain this QAOA, but I'm not sure if.
I believe, so in my opinion, it was a very good explanation. So,
because I didn't find that explanation anywhere. It just I came to it by playing with QAOA. That's why I want to share it with you, because I'm not sure if. Okay.
I know that at least several participants are familiar with QAOA as well, and VQE. Okay, I don't see any questions now on our chat, and there are no raised hands. So. Adam, you can ask your questions.
Okay, thank you. But Kasia, if that's not a problem, I would like to see the presentation, because I have most of them are directly connected.
Okay. Okay. Yes.
Could you first go to the slide where you present the binary encoding?
This one?
No, the binary encoding of the integer number. I think there was something like the sample to the something.
This one?
Exactly. The 4 flag variables. So I think the nice thing is that there's a little bit better way of how you can choose the encoding. The thing is that with this encoding, most of the numbers, many of the numbers written this way are not allowed even for the slack variable. So for example, imagine that slack variable can be at most 2. Then with this encoding, you can also produce value 3.
Yes, I know. Yeah, there are many incorrect encodings. Yes.
Yes, I mean, it's almost half of them. So it's, in general, it may not be a problem, but if you have many slack variables, then it starts to grow exponentially. There is a trick well known by both Qiskit and PyQubo. so that the largest wave, instead of being power of 2, is the maximum possible value minus maximum possible value for slack minus maximum possible values which you can produce through all the other bits.
Okay,
it sounds a little bit complicated, but it's very
yeah. I think we saw it with Justyna because we're searching the CQM library and we came across this. I think it's the same thing, that you code slack variables all except the largest one you code normally, and then the largest one you code with different coefficient, with smaller
exactly.
coefficient.
You use the same number of circuits, but the wave is a little bit smaller, which is also good.
Yeah.
But also all possible values you can achieve are in fact good for the slack.
Yeah.
So it's just a hint. Qiskit and PyCubo are doing this just naturally. So
yeah, I think CQM is already present. So yes, okay.
Okay. As for CQM, this is another thing, is that my guess, but it's only a guess, is that CQM is quite good because it is very, very classical. The thing is that data about this algorithm are not known. They are hidden. They are private property of the D-Wave company, but we are investigating a different problem of the vehicle test production from BMW. And we're in fact comparing PULP, Girobi, and CQM. Girobi was clearly the best, both in the quality of the solution at the time, but I must say that CQM was not that far away. Mm-hmm. But if you would look at the time which was used by classical quantum computation, because this necessarily hybrid algorithm, then you can see that quantum part is extremely small. It's like, I think it's even below 1%. I will soon, actually my colleague will soon push the preprint on this result, so you may check this by yourself. I myself don't remember the exact values. So I would say that this is why CQM is good. And there's one more thing. What is important? CQM can accept inequalities. You don't have to provide QBO.
Yeah, I know. We already go through it because we were looking at the code of this CQM, which is open, and we actually by looking at that we found out this slack trick with with this coefficient. Yes, so yes, you can add here their inequalities and it will transform it somehow. But I'm not sure if I know exactly how it just adds slack.
No one knows.
Sorry?
No one knows. No one knows how CQM works.
Oh, okay.
And because there's a solver hybrid which can transform it into QBO and then solve it. But CQM, no one knows. It just takes the problem and somehow it solves it. They claim using quantum computer. Mm-hmm. I actually trust them that they may be using quantum computer. The thing is how significant is the quantum part for the whole computation, but that's a different story.
Yeah, that's true. That would be useful to know because otherwise it's really black box and you
black
don't
box.
Know. Yeah.
Mm-hmm. So a question: how much time do we have?
Now
we are not bounded, Adam. So we can. So usually we want to finish in 90 minutes. So we can say that we have 25 minutes left, but.
Okay. Then perfect. I don't have that many comments. Okay, so there, Katarzyna, you had a table in which you compared VQ and QAA.
Yeah, I have it. Where do I have it?
I think it was 30. Slide 30.
Yeah.
Or 29. That's close. Okay, so you are comparing VQ and QAA. However, if you're thinking in a combinatorial optimization problem, then most of these neighboring cells are in fact the same. For example, you still measure only in the Z basis.
Yeah. If you, well, it depends on your problem Hamiltonian. In the combinatorial problems, Hamiltonians are diagonal. So you can put here diagonals and you don't need to measure other basis.
Exactly.
Yeah,
I guess you know about it, but for the audience, I found it would a little bit confusing. So I would
okay. So maybe this comparison is not perfect, but yeah.
And the comparison is perfect. It's just not good for just for problem. It's if you think about this in general. But still, it's very nice. But now I would like to go to my more significant concern about these paths. So I have paths, exactly, the number of paths. So imagine the following workflow. You start in a fixed node, and then you have a layer with 2 nodes, and you can choose any of them. Then you put another layer with again 2 nodes, and you can, from the previous level, you can go from any to any.
Yeah, with binary tree or any other tree like that, it would be a disaster. Yes, you're right.
So it's not a tree, it's duck, for sure.
But the tree is also duck, isn't it?
It depends how you define tree.
Anyway, go on because it's not the main point.
But anyway, with this construction, having one linear number of bits, tasks, you have already exponential number of paths.
Yeah, and that, yeah.
And this problem will arise in any case if you have like such linear sequence of layers, and each layer will have at least 2 cells. Even if, let's say, half of them will be at least 2, it is already a problem. Yeah. But I think I know how to solve this. And the way is, okay, I would call it in general through some like time windows. So the way I understand the problem is not that each path has to be below the deadline, but each node should be, how to say it, considered by some machine before the deadline, right?
That's true.
So instead of producing inequalities per path, you just need to rebuild this problem so that you have these inequalities below the line per task. I'm not saying that this is trivial to do this, but I myself, me, Ozlem, and Jarek Miszczak make a paper in which we are making time windows, but for traveling salesman problem. I believe that at least some concepts from this could be used here.
Okay.
Obviously, it's more complicated because we have like one cycle which we should have to think of, and you have like more unstructured thing. Still, I'm pretty sure it should be possible to construct it this way.
Yeah, so we definitely look into this because reducing the number of variables, well, our solution works well if you don't have too many paths and you don't have this structure as you described. Yes, but yes, any way to reduce the binary variables number is good to investigate. Yes, so definitely we'll look into that. Yeah.
And what's more is that this is something which is not clear to me, to be honest. But I also think that you can create a better integer programming also from the encoding itself. So you are saying that what you are doing is that you are making binary variables ti. So the same machine task t is made by exactly like in this table. Is made by machine I. I'm choosing 2 indices. I think this is a little bit simpler to see it this way. But at the same time, each task can be assigned to only single machine, exactly single machine, right?
Yes.
So what you actually have is that you have a function from task to machines. This is like higher abstraction level.
Yeah.
And what you're doing is that you are encoding this function using the one-hot encoding, at least here. And I'm not sure what you are doing at the very end.
Yes, it's one encoding, and Julia and Asia did also binary encoding and domain well encoding for this. So changed it into the domain wall and binaries, and they will tell you about that later in next.
Okay, but like a quick question: did you manage to make a binary encoding with still having a cubo without quadratization? Or did you result in higher order?
As far as I remember, it was higher, but I think Julia is present on this seminar and she can answer, but I remember it was higher. Yes, Julia?
Was the quote about which encoding are you asking?
Binary.
Well, yeah, that's dependent on the number of machines, right? So
sure, but was it a higher order in an optimization problem or quadratic?
Well, the order of the polynomial is dependent on the number of machines. So when we had 3 machines, that was still quadratic, I guess, because you need 2 bits to encode 3 machines. So it didn't grow as much for us because we didn't try very big examples, but with larger examples that would grow.
And because with that, there are 2 ways you can go with binary encodings. First is which I guess is you use from my paper about this Hobo encoding, when you have these delta Hamiltonians, but there's also alternative way in which you just treat this as integers, look for integer linear program, and then, or quadratic integer program, this is actually fine here, and then transform it the usual way into cubo. And the latter approach I was usually doing by surfing the internet and looking for my problems, the already known inter-linear problem, but I'm pretty sure that for workflow, there should also be an inter-linear program which you can transform. I'm not saying it will be better, but it is always, in my opinion, it's also always worth trying to look for such a representation, because it's often not so bad.
Yeah, but it would be nice if you can pass us the source for this, because I could not remember all the steps.
Sure, I guess it to be.
It's recorded just in case. And Adam, are you in contact with Kasia by email or?
Yes, we are in contact.
Yes.
So you can just follow up after the meeting. So that's fine. So yeah, if you could share your papers and your ideas with Kasia, then I believe that it can be very beneficial for the Polish science and maybe even world science. So
and for EuroHPC project.
And for EuroHPC project, that's correct. Great. Yes. Any more questions, Adam?
No, I think I have enough of them.
All right.
There were more suggestions than the questions, but we are very happy that we have such suggestions, because we can go on with our problems.
So just in case, everything is recorded and will be available on our YouTube channel after you confirm and approve the video, of course. So you can go back to this discussion. So I'm also very happy, and thanks, Adam. Really great suggestions and great discussion. So. All right, maybe some other questions or some other suggestions from other participants. I don't see more questions or suggestions now or raise hands. So Kasia, thank you once again. It was a very interesting lecture and very interesting and inspiring discussion as well. Just before the end, I will just share my screen once again to present some final slides and introduce the next event. I hope you can see my screen now. So first of all, we would like to thank once again our strategic partners, Starto and Cogit, and our honorary partners as well. And we would like to invite you to attend our next meetup that will take place in just 2 weeks from now, 28th of February. And as Kasia has said, it will be, as far as I understand, some kind of continuation of this talk, right? So this will be a talk given by Julia Plewa and Joanna Sienko. So in fact, Julia is probably still with us. So Julia, would you maybe like to briefly advertise your lecture?
Okay, I didn't really prepare for this,
yes,
but I can.
You can try.
I can try. Well, what we did for our masters is that we sort of expanded on the results that were presented in this presentation. We simplified some of the definitions. So yeah, some of the questions that Adam was asking. Well, maybe they weren't necessarily addressed, but some things were done a bit differently. And we introduced different encodings. That was, I guess, the biggest change, because in the older work, everything was done with one-hot encoding. And we sort of played around with different versions to see which one performed the best. And yeah. Okay,
yeah, fair enough. Great, very nice introduction. So thanks, Julia. So we are looking forward to your talk in 2 weeks from now. All right. So as I said, we'll hopefully we'll upload the video to our YouTube channel soon. And after this meetup, I will also send a survey to all of you. If you're interested, let's stay in touch. Please feel free to join our groups, mailing lists, follow our fan pages, profiles, channels, and so on. And that's all for today. So I will now stop recording.